Remember the 5th of November. 6.1, systems of equations in two variables. So there's two things we want to do. We want to solve a system of two linear equations by graphing, and then solve same system of two linear equations by using substitution and the elimination method. So we're going to show you three methods. Method number 1, graphing. Method number 2, substitution. Method number 3, elimination. And all of them are designed to do the exact same thing. Take a set of equations, 5x minus y equals 5, and 4x minus y equals 3, and find a solution. Find an ordered pair, x and y, that make both equations true. And in this case, they kind of give you the answer. They tell you that the pair is 2, 5. So if you take x equals 2 and y equals 5, and you substitute them into equation number 1, it makes it true. And if you substitute them into equation number 2, it also makes them true. Graphically, we're talking about graphing one line that maybe looks like this, and graphing a second line that maybe looks like this, and figuring out where they intersect. That intersection point is the solution. In this example, we have two equations, f of x equals x plus 1 and g of x equals negative x plus 3. And so for f of x, we're going to write this in red, like a fox. G of x, we're going to write that in green because G is for green. So we'll have an x and f of x. And we're going to pick 5 points, negative 2, negative 1, 0, 1, and 2. And so when we plug in negative 2, that becomes negative 2 plus 1, which equals negative 1. And you get a graph that looks something like this. So this would be f of x. And the red line represents all the solutions to f of x. All of these ordered pairs are solutions to the function. Let's do the same thing for g of x. The graph that we have appears to intersect at a certain point right here. And that point appears to have coordinates of 1, 2. If you look at the table, you'll notice 1, 2 is in f of x, and 1, 2 is also in g of x. The solution has the exact same x coordinate in both tables, and the exact same y coordinate in both tables. In other words, the x coordinate from the red function equals the x coordinate from the green function, and the y coordinate from the red function equals the y coordinate from the green function. This is important. It's saying that the x's in both equations are the same and the y's in both equations are the same. So we're going to use that to our advantage in this example. Here we have f of x equals x plus 1 and g of x equals negative x plus 3. This is the same problem we just did. But now we're going to solve it without the graph. We're going to solve it using substitution. So we're going to rewrite this first equation as y equals x plus 1. And we're going to rewrite the second equation as y equals negative x plus 3. And what we just talked about was saying that the y coordinates are the same. So the y's, so you could write x plus 1 equals y, which equals y, which equals negative x plus 3. This equals that equals this equals that. And you can summarize this by saying x plus 1 equals negative x plus 3. You basically take what this y is equal to and you substitute it into the green equation. So everywhere you see a y in the green equation, replace it with x plus 1 from the red equation. This is 2x equals 3 minus 1, 2x equals 2, x equals 1. This is only half of the ordered pair. So we need to take this answer and back substitute to solve for y. So we know we did it right, because it doesn't matter which one we plugged it into, we got the same answer. So your final answer is 1, 2. That is the coordinate, the location, where these two lines intersect. And if we go back to our example, yep, that's where they intersect. 1, 2. So we got the same answer. Let's do this on a system that we don't know what the answer is. So here's a new system. Again, I'm going to say y equals 6 minus 2x. And then the second one is 3x plus 4y equals 4. And this one's kind of nice because This is already set up for me. Y equals 6 minus 2x. So we're going to take this y and we're going to substitute it into the second equation. So the second equation will become 3x plus 4 times y. And what's y? 6 minus 2x equals 4. And now distribute. X equals positive 4. Once you have x equals 4, you're still not done. You have to back substitute this into the original equation to solve for y. So y equals 6 minus 2 times x, which we determined to be 4. Put them together and you get 4 comma negative 2. That's your ordered pair. That's the intersection point. That is the solution to the system. So it's really nice when, like in the previous example, the equation is set up for you and it tells you y equals something or x equals something. This one, it's not the case. They don't come out and tell you y equals something. Instead, there's a 3 in front of the y and there's a 2 in front of the x. So what we need to do is manipulate one of the equations, solve it for a variable, and then substitute that into the second equation. So let's start with the first equation. This is 2x minus 3y equals 18. Flip a coin. What variable do you want to solve for? X. Okay. So we're going to say 2x equals 3y plus 18. Divide everything by 2. And we'll get x equals 3 halves times y plus 9. So that's what x is equal to from the first equation. Sometimes when I write these, I'll say x sub 1, just to remind me that this came from the first equation. And now we're going to take this and we're going to plug it into the second equation, which is 2 times x plus 3y equals negative 6. And what is x? It's this stuff. Distribute the 2. Y equals negative 4. We now take this and back substitute it to solve for x. So that means x equals 3 halves times y, negative 4, plus 9. X equals 3. And now write your solution as a nice ordered pair. 3 comma negative 4. Sometimes doing substitution when you are given things that you have to manipulate a whole lot of is a very tough process. There is a third process that we can incorporate. Focus back over on these equations here, and we're going to add them up. 2x plus 2x is 4x. Negative 3y plus 3y goes away. Equals 12. X equals 3. You could say 2x minus 3y equals 18, and you could take the second equation, multiply everything by negative 1. Negative 2x minus 3y equals 6. And when you add these together, the x's cancel, and you get negative 6y equals 24, y equals negative 4. And now we have both coordinates. This technique of adding equations is called, guess what? The addition method. It's also sometimes called the elimination method. And the reason they call it the elimination method is because your focus is to eliminate a variable. You want to rig the equations so that way a variable gets eliminated when you add them together. In other words, one coefficient is a positive number, the other coefficient is the opposite of that number. So here we have two equations. If you look at these two equations, you'll notice neither variable eliminates. Like the x's won't cancel if we add them and the y's won't cancel if we add them. So we need to manipulate one or both of the equations in order to get rid of a variable. Let's first decide what variable to get rid of. Flip a coin, x or y. I heard y first, so we're getting rid of y. Okay, so we're going to get rid of y. So what we need to do is multiply this top equation probably by the number 3. So that's going to become 9x plus 6y equals 72. For the second equation, we need a negative 6. So we're going to multiply everything by negative 2. So that'll give us negative 4x minus 6y equals negative 52. 9x minus 4x is 5x. The 6y's cancel. They eliminate by design. Equals 72 minus 52, 20. X equals 4. Back substitute into either one of the equations. We're going to back substitute into both just to show you that it works. And so we're going to say 3 times 4 plus 2y equals 24. Y equals 6. Now if we've done this correctly, we should be able to substitute into the second equation and get the exact same y coordinate. 2 times 4 plus 3y equals 26. Y equals 6. So our final answer is the ordered pair 4, 6. This is the exact same problem. Instead of eliminating y, let's eliminate x. So we're going to take the first equation, we're going to multiply it by 2. We're going to take the second equation, and we're going to multiply it by -3. Our x's are going to cancel by design. We intentionally did that. So we get -5y equals -30. Y equals 6. Take that value, back substitute it into one of the other equations. X equals 4. Our solution is 4, 6. Exact same solution. When you're doing these types of problems, there are 3 possible scenarios you can make with 2 lines in a plane. Scenario number 1 is going to happen about 80% of the time in this class. Most of the problems that you see are going to be of this type. They're going to have one solution, and that solution is going to be an ordered pair xy. And you're going to do either substitution or elimination. You're going to get an answer like x equals 3 and x equals 4. This type of system is called consistent and independent because it has exactly one point that is common between the two of them. It has one solution. Scenario number 2 is going to happen about 10% of the time. And this is when the 2 lines are parallel. When the 2 lines are parallel, they have no common points and there's no solution. And these are called inconsistent and independent. When you try to solve an equation like this using substitution or elimination, you're going to get an answer like 3 equals 5 or 0 equals 2. You're going to get answers that don't make sense. You're going to do all of your math correctly. You're going to do the substitution correct. You're going to distribute and solve for x and do all this, but you're going to get these goofy looking numbers like 3 equals 5. And a lot of students say, I must have done something wrong, let me go back and check my work. And they check their work and they get 3 equals 5. I must have done something wrong, let me go check my work. They check their work, they get 3 equals 5. They can't understand why they keep getting 3 equals 5. What they're failing to do is interpret the results. When does 3 equal 5? Never. When do these lines intersect? Never. So that's why you get these goofy answers. If you solve an equation and you get 3 equals 5, recognize what it's telling you. These lines never intersect. They must be parallel. The third scenario you can have, which of course happens again 10% of the time, is that you're dealing with the same line. You can't quite see it, but there actually is a blue line underneath this red line. The lines are stacked one right on top of the other. And this is called being consistent and dependent. And so what does this look like? What do these type of solutions look like when you try to solve them? So you're solving an equation and you'll get something like 3 equals 3, or 0 equals 0, or x equals x. When does 3 equal 3 and 0 equal 0 and x equal x? Always. Everywhere. Where do these lines intersect? Everywhere. It's one line right on top of the other. There is an infinite number of solutions. So 80% of the time you're going to see situation number 1. So get used to it. But every once in a while, just to keep you on your toes, we're going to throw a number 2 and a number 3 at you, just to make sure that you understand what's going on, that you can recognize parallel lines or the same line. If 2 is good, 3 is better. So now we're going to solve a system of 3 equations. And something you want to notice right away. First of all, we've added a third equation. We've also added a third variable, z. You're going to glass over the 3 equations and see, is there a variable that looks like it would be easier to eliminate? X looks pretty good. Y's not bad either. I wouldn't mess with Z. I'd stay away from Z, right? There's too much to do there. I'm going to take equation number 1, equation number 3, and I'm getting rid of X. This is going to get pretty complicated, and you want to be able to keep track of your thought process and all the action that you're taking on these equations. So we're taking equation number 1, equation number 3, and we're going to add these up with the intent of getting the variable X to eliminate. So we get 3y plus 3z equals 3. And look at that. They all have a factor of 3 in them. So let's divide both sides by 3. This is equation number 4. So this time I'm going to take equation number 2 and equation number 3. I'm going to get rid of X. It's important that the variable that you get rid of matches. This one we got to do some manipulation. So equation number 2 is okay. Equation number 3, however, we have to multiply that by 2. So we're going to multiply equation number 3 by 2. So with intent, the x's are going to cancel, leaving us with 3y plus 9z equals negative 3. Once again, we have a factor of 3 in each term, so let's divide everything by 3. And we're going to call this equation number 5. So now we're going to take equation number 4 and equation number 5, and we're going to get rid of another variable, y. So maybe I'll take equation number 4 and just write it as is. And I'm going to take equation number 5 and multiply it by negative 1, and we're going to add those together. By design, the y's are going to cancel. Negative 2z equals 2, or z equals negative 1. So what you found here is one of the 3 coordinates. You found the z coordinate. Take this z coordinate and back substitute to solve for y. So y has to equal 2. And now that we've got a z and a y, take both of these coordinates and back substitute into an equation up here. So this leads us to x plus 1 equals 2, or x equals 1. So now we can write our answers in ordered triple. 1, 2, negative 1. Here's an example of the type of three-dimensional solutions you can have. So this is like the problem that we just did. Instead of dealing with lines intersecting, you're dealing with three-dimensional planes, three-dimensional sheets of paper intersecting. And so here we have equation 1, 2, and 3, and they all intersect at a single point. So there's one solution. On the second one, there is no place where the 3 planes intersect. 1 and 2 intersect here, 2 and 3 intersect here, 3 and 1 intersect all along here, but there's no place where all 3 of them intersect. 1, 2, and 3, they're all parallel. They're all parallel sheets. They don't intersect. Here's one with infinitely many solutions. In this case, planes 1, 2, and 3 all intersect on a single line. Planes 1, 2, and 3 are all on top of each other.